particles in spherically symmetric potential. This problem is useful for the Coulomb potential. For example, if we have positively charged ion in the center or origin, and you have electron, there is Coulomb attraction potential proportional to 1 over r. So the potential is a pure function of r. So previously we considered the rectangular coordinate consisted of x, y, and z. But this Coulomb potential is described by the independent variable of r. So we change the coordinate like r, theta, pi coordinate, and we call this as spherical coordinate. And when you solve this Coulomb potential problem, then you will have 3 different quantum numbers. Because it is 3-dimensional problem, you should have 3 different quantum numbers. So this is 3-dimensional coordinate and another 3-dimensional coordinate. The 3 quantum numbers are listed here. N, principal quantum number. L, orbital or angular momentum quantum number. M, whose condition is given here. The absolute value of M is larger than L. M is z directional angular momentum quantum number. So actually that's it for today's course. We just remember 3 different quantum numbers, and you remember their conditions. N starts from 1, 2, 3, and so on. L starts from 0, going all the way up to n minus 1. This condition, absolute value of M larger than L. But to induce this, you need to go through some mathematical procedures, which is not the most important part of this class. Mathematical procedure might look complicated, but still it is okay even though you cannot induce that, as long as you remember this. So, introduction to 3-dimensional Schrödinger equation. Until now, we solved those quantum mechanical problems only in 1D. Here we extend it to the case of 3D. First in rectangular coordinates, followed by spherical coordinate. We will eventually study excitonic problem, which is one of the most important issues in optoelectronic studies. Exciton is the pair of electron and hole under Coulomb attraction. So one positive charge, one negative charge, and it is almost the same with hydrogen atom problem. We know hydrogen atom. There is one electron in the orbit, and the proton has one positive charge. So electron and proton, they are under Coulomb attraction. That's the way they form hydrogen atom. And exciton is similar to hydrogen atom, but their scale is quite different. Exciton is very large. Hydrogen atom is relatively smaller. That is one of the most important problem for the spherical coordinate. Anyway, we first discussed the Schrödinger equation in 3D for the case of free particle. So the Hamiltonian composed of kinetic energy part and then potential energy part. Here, let's say potential energy is 0, so we presume the particle is free. Then Schrödinger equation becomes simple like this. We solve it. We divide both sides by minus h bar square over 2m. Then this energy is replaced by minus k square. When the energy E is defined h bar square k square over 2m. And here round the square, round x square, round the square, round y square, round square, round g square. It's called as Laplacian. Okay, when we solve this, we set wave function of psi to be x, which is a pure function of x, y, which is pure function of y, and z, which is pure function of z. So they are only described by certain independent variable x, y, or g. We put it into here. Okay, then we got this. Okay, then we divide both sides by x, y, z. Then we get that x double prime over x, y double prime over y, g double prime over g is equal to minus k square. K square is formed by kx square plus ky square plus kg square. So that we set this x dependent part to be the same with minus k square. Likewise, y dependent part will be minus ky square. G dependent part will be minus kg square. So we can set x double square over x is equal to minus kx square. And repeat this for y and z. And then we have solution. The most general solution will be a prime e to the I kxx plus something else. Here there should be minus I kx x for the general case, but let's just consider right propagating wave only for simplification to make it simple. Okay, so let's ignore this part. For y, let's say we have this b prime e to the I kyy, z prime e to the I kzz. Combining all three factors x, y, and z gives the solution like this. A prime, b prime, c prime, they are multiplied together in the other part. And here, this one exponent is replaced by I k dot r. Okay. The wave vector component is here, and position vector is here. And each Schrödinger equation for different axes, x-axis, y-axis, and z-axis, can be solved also separately. And now let's say we apply the sine cosine representation. Then x could be represented like a sine kxx, b cosine kxx. Then if we set the potential is 0 from 0 to A along x-axis, then we know wave function psi should be 0 here at x equals 0. No, x equals A, I'm sorry. And also wave function psi should be 0 at x equals 0, right? Should be 0 at x equals A. Right, so if we consider the three-dimensional box, so it's like a K here can exist only within the box. Outside it cannot exist. Okay, so potential is infinity outside in that case, and 0 inside. So the inside we are just the same with the case of free particle. That's why we use the previous equation. So for x, generalized solution is given here, and we apply boundary condition. So at x equals 0, at x equals A, it should be 0. So at x equals 0, we only have b cosine part. So b should be 0. And x equals A, you apply this, then you have A sine kx A. It should be 0. It means kxa should be n phi, so that sine function is 0. Here n is the integer. That's the way we determine x to be the same with a sine like this. Yeah, so kx is replaced by n pi over a here. So kx is replaced by this. Yeah, similarly, y is given b sine ny pi by, and this is the scale of the box along y-axis. For g, yeah, it is c multiplied by sine ng pi over cg. So we multiply them, x, y, and g. We multiply them, then this abc, the coefficient becomes large n because three different coefficients. Let's say it is multiplied. Then let's set it to be n. Another, yeah, x, y, g related sine functions are multiplied. And then for the normalization condition, you can get this. Yeah, basically we integrate this in 3D space. But outside the box, wave function is 0 anyway, right? So inside box, we integrate this, then we can calculate the n. Anyway, n is determined to be square root 8 over abc. Depending on the energy, which is h bar square k square over 2m, and this is k square, and kx, ky, kz, they are replaced by this, like this, like this. Okay. And then we introduce the spherical coordinate. So x, y, z coordinate is replaced by r theta phi coordinate. Please read through yourself. Okay. And this is useful for Coulomb potential, like this, because it is a function of r, right? It doesn't depend on theta or pi. It only depends on r. For such potential, rectangular coordinates are inconvenient, right? We don't have x, y, or z dependence here. We only have r dependence. So spherical coordinates are a better fit. Spherical coordinates are defined in the figure on the right, yes. So x, y, z is given here, g equal to r cosine theta, y equal to r sine theta multiplied by sine phi. So basically like this is theta, this is pi over 2 minus theta, right? So for the length of r, we take this, then we get this value. This value is actually r sine theta, and then we take the cosine, then we have x value projected into x-axis. So r theta pi, r sine theta, then cosine pi, this is x. Likewise r sine theta, and then we multiply it by sine pi. Okay. G r cosine theta. And this is actually taken from the undergraduate advanced math course. So XYZ is defined here, and depending on that you can calculate round x, round y, round z. You don't need to calculate yourself. Probably you already have done this in undergraduate course. We just accept that this one, same with Laplacian, and Laplacian is represented like this in spherical coordinate. So we just accept that, and we put this into the Schrödinger equation. So previous Schrödinger equation has the Laplacian part, and it is replaced by this r theta pi representation like this. So we just accept this instead of calculation. Okay. So this is Schrödinger equation. Okay. In spherical coordinate. So we see that this is the kinetic energy part, and this is potential energy part, and this potential will be replaced by the Coulomb potential eventually. But before that, let's say we don't know the potential shape yet. Then we separate the variables like this. Wave function psi is replaced by pure function of r, which is large r, and then angular part y. Then we put this into here, and into here. Okay, so wave function psi is all replaced by r y. Okay, so r y. This is pure mathematical function for r, so y is independent. Here is pure function of theta, so y is here, r is outside. And then this is again the angular operation, so r is independent, so it is coming out over here. Okay, and then this right hand side, e multiplied by psi, and this one goes to the right. So E minus V multiplied by Ry. Okay. And then we divide both sides by this one. Minus h bar square over 2m multiplied by Ry. Okay. Then this one subtracted by this one and divide by Ry. So eventually you got this 1 over r, and then r operation. Then there's 1 over y, and then zeta dependent operation, zeta and pi mixed up. So this is actually very tedious calculation, but everybody can do that. It's just straightforward. Okay. So try yourself. Okay. Well, if you cannot try it yourself, still it's okay, but I'm pretty sure everybody can do that. Yeah, and then it is arranged like this. Okay, here the left hand side is pure function of r, dependent part. Right hand side is zeta phi dependent part. But you can easily see that this r dependent part somewhere right like this. R dependent part. Yeah. Here, R dependent part. Okay. If we divide both sides by, we multiply it by R square. Yeah. To make it simple. Okay. Multiply by R square, then R square, R square, R square. Yeah, they disappear. Then it becomes simple. So pure function of r, pure function of zeta phi should be the same, means they are actually both constant. Okay, let's set it to be lambda. Then this left hand side, same with lambda. Right hand side, same with lambda. Alright, so this r-dependent function is called as radial equation, and zeta phi dependent function is angular equation, and then we calculate them separately. It looks quite complicated, but as I said, it is still okay as long as you remember the three different quantum numbers, n, l, and m. Actually, radial equation gives you the principal quantum number m. Angular equation will give you L, m. But even though you cannot induce this, still is okay, right? We calculate angular equation first. So this is the angular equation part, and y is also a function of zeta and phi. So let's separate them, like f, pure function of zeta, g, pure function of pi. Okay, so put it into here, and then we go through the similar procedures. Yeah, we divide both sides by fg, and then look at this. This is f is pure function of zeta. Look at this. So we have just zeta function here. Then there's sine square here. And then the others are pure function of pi. So we set this pure function of pi part to be the same with minus mu. Then we got this. Equation 3. This is actually very simple. The rest of the equation now simplify like this, because we set this to be minus mu. Then you have this minus mu function here, minus mu part here, minus mu part here. So from equation 3 you got this g. So it's like let's say Yeah, we take the derivative with pi, so g prime equals minus mu g. So this is the case when we have like something like this, right? So we got this. The general function is if mu is not zero, okay? So you take the second derivative and you have original function. It means it is exponential function, exponential. So we have exponential. So this is most general solution when mu is not zero. When mu is zero, second derivative is zero. So g is the linear function of pi. So most general solution is a plus b pi. Right? And then g is continuous from 0 to 2 pi. It means the 0 and 2 pi, it is boundary. It's repeated. Okay, again and again. So every 2 pi, equation should have the same result. So we set this into here. So a plus b, and then we put 2 pi here, 2 pi, 2 pi, and 4 pi, 4 pi. They should be the same endlessly. It means the square root of mu should be certain integer. Okay, certain integer. So let's set, like this, mu to be like m square, and m is the integer. Okay, and also we consider the normalization condition. Okay, so that we can determine the constant a. Then we replace the mu by m square. Okay, mu is now replaced by m square. Then we got this zeta equation. Here things are a little bit complicated, so if we introduce omega to be the same with cosine zeta, then things will be quite simple. So let me show you how. Okay, so for example, t zeta is actually same with, if we change it with this w function now, then you need to integrate differentiate w by zeta like this. Then w is set to be same with cosine zeta, so it is minus sine zeta t w. Okay, so you can easily divide both sides like this. So this goes to the left, and you ignore this part for now. Then you get the 1 over sine zeta here. Same with dw, right? So this one like this, then this one like this, we consider separately, and this one is replaced by round w or omega. It's just the same, you just introduce the other parameter, the other variable here. So let me call it just w here. Okay, So round W, and here sin theta, 그다음에 then round theta. Okay, sin theta, round theta. This is same with this sin theta, and the numerator we change it like a sine square theta over sin theta, round theta, and this one is same with the 1 minus cosine theta square, so it's 1 minus w square, then sin theta. So this one changed like this, okay, and this one same with this. So you can make it simple like this way. So this is just the mathematical procedures which was solved by some physicists in old days already, and this mathematical equation now we so actually I use these procedures, please refer to this. So now we have this equation, so theta equation replaced by this one. It is called as associated Legendre equation, and we don't need to calculate it ourselves, but we just know the meaning, okay. This associated Legendre equation has the solution only when lambda equal to L plus 1, and this L is actually the angular momentum quantum number. We put it into here and then solve the equation again. Then we found if m is 0, the solutions are called Legendre polynomial. Yes, and could be 0 because there is solution. There is a solution. So, or m could be non-zero, then it should satisfy this condition. Okay, this L is named as total angular momentum quantum number. If based on this condition, if L is 1, m should be minus 1, 0, plus 1. The solutions for non-zero m are associated Legendre functions. Like this. You don't need to remember this. You will just use this from the table. Okay? So in this way, the angular solution y is given like this. Y is actually depending on what kind of quantum number L, what kind of quantum number M you have. So we have this L-M dependence, and it is replaced like this. P function and previous G function, they are multiplied, and there's normalization constant. And we list some of the this solution y. This solution y is called as spherical harmonics. Okay? It is often found in some of the research papers too. So when L and M, they are both 0, it's 1 over square root of 4 pi. When L is 1, M could be plus minus 1, then the equation is like this. When L is 1 and M is 0, then it's like this. So look at this. This is the case when M is 0. Okay? L is 0. This is those three cases are actually L is 1, okay, and there are 5 different cases, plus minus 2 different cases, and there's another one. So there are actually 5 different states. 5 different states here. 4 L equal to. So you don't need to remember this, but you just see the structure, right? And the meaning of the angular equation and its solution is explained here, but the point here is we have discrete number of quantum numbers. There was L and M. Those are important quantum numbers. Okay. Others are actually very simple. Actually, you can easily read through this. Okay. The L is the angular momentum in classical physics. It's calculated to be mr squared, and omega here, omega is the angular velocity. Okay. In quantum mechanics, however, we can only calculate L squared. It is same as L plus 1 h bar squared. Okay. And if we project angular momentum into g-axis, then you have LG. LG is the same with mh bar. That's the result of quantum physics. Okay. So just like I said, it looks quite complicated at first, but still remember that there's principal quantum number n, angular momentum quantum number m, L, and then g direction angular momentum quantum number m. Okay. Right. So today actually I have some pain from my knee, so you might see I'm not fully, what should I say? Yeah, functional. I'm not perfect in explaining things, but still you figure out the meaning of 3 different quantum numbers. And how can you get that principal quantum number n? That we will discuss next class. Okay, that's it for today.